Welcome back to educator.com. This is linear algebra, and today we're going to be talking about determinants. Determinants have Determinants are a very, very curious thing in mathematics. Obviously, they play a very big role in linear algebra, but they also play a big role in other areas of mathematics. Now, we're not going to necessarily be dealing with too many of the theoretical aspects. We're going to be more concerned with computation, using them to actually solve problems. But it is good to know that determinants are a very, very deep part of mathematical research. Let's go ahead and get started. Okay. Let us take a matrix A, and we'll use our notation A11, A12, A21, A22. Okay. 2 by 2 matrix. We define the determinant of A. Another symbol for the determinant is a straight line up and down. We will be using that symbol. We'll be using both interchangeably. A12, A21, A22. So it depends on what it is that you're talking about. You use the lines when we want to specify the entries. We use this more functional notation, determinant of this matrix A, when we want to simply speak about it in the abstract. So we define it as A11 times A12 minus A12 times A21. The pattern is this times that minus this times that. Again, A11 along the main diagonal, this times that minus that times this, including the signs. Let's do the same for a 3 by 3, and then we'll do some examples. So let's say that B is our 3 by 3, so we have B11, B12, B13, B21, B22, B23, B31, B32, B33. Linear algebra is notationally intensive. Okay, now the determinant of B is equal to, okay, I'm going to write it out, and then we'll talk about an actual pattern that you can use. B11 times B22 times B23 plus B12 times B23 times B31 plus B13 times B21 times B32 minus B11 times B23 times B32 minus B12 times B21 times B33 minus B13, B22, B31. Here is the pattern. There are different ways to think about this, and I know that many of you have, of course, seen determinants before, back in high school and perhaps in other areas of mathematics, perhaps in some college courses in calculus or something like that. Here is the general pattern. Notice we have some that are plus, 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 and some that are minus, minus, minus. This first one is B11, B22, B33. Going from top left to bottom right, multiply everything down this way. The second entry, just move over and go down again to the right. B12 times B23, but since you have nothing over here, just go down to this one because you need 3 entries. Notice each one of these has 3, 3, 3, 3, 3, 3. You need 3 factors in the multiplication. So it's this times this times this. Now you go to the next one. B13, there's nothing here, but you need 3 of them. So you go here and here. So it's B13, B21 times B32. That takes care of the plus part. Now let's deal with the minus part. Go back to the B11. Well, B11, now try going down to the left. Well, there's nothing here at the left, but you need 3 terms. So it's B11, B23, B32. Go to the next one over. B12, B21, there's nothing here, but there's one here, B33. B13, B22, B31. There are different kind of patterns that you can come up with. This is simply the best pattern that I personally have come up with to work with 3x3s. Again, you've probably seen determinants before, so whatever pattern you come up with is fine. I think this works out the best simply because you're going to the right, positive, you're going down to the left, negative, if that makes sense. So those have positive signs. When you're moving in this direction, you have negative signs. And of course, in this, you have a 3x3. Each term has to have 3 things multiplied by each other. Okay, let's do some examples. Let's go back to, actually, you know what? I think I'm going to try blue ink. Let's define A as 1, 2, 3, 2, 1, 3, 3, 1, 2. Okay, so let's do our pattern. Let's see, let's go ahead and put something like that. And we'll say the determinant of A, okay, 1 times 1 times 2. It's 2. Okay, plus 2 times 3 times 3. 2 times 3 is 6. 6 times 3 is 18. Plus 3 times 2 times 1, 6. Okay, now minus 1 times 3 times 1. It's 3. Minus 2 times 2 times 2. 2 times 2 is 4. Times 4 is 8. Close this 8 off. Minus 3 times 1 times 3. Minus 9. When we add them all up, hopefully my arithmetic is correct. Please check me. You should get 6. So again, positive this way, negative that way. Okay. Let's do a 2 by 2. Let's say B is equal to 4, negative 7, 2, negative 3. So now we have some negative entries. Okay. The determinant of B is equal to this times this. 4 times negative 3 is negative 12, minus this times this. This times this is negative 14. The minus sign has to stay. So it's negative 12 minus a negative 14, minus 12 plus 14, it is equal to 2. Okay? So these signs here, this plus here, plus here, plus here, negative, 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 they always stay there. It doesn't matter what these numbers are. If this is negative, then a negative times a negative is positive. But you have to have 3 positive terms in a 3 by 3. You have to have 3 negative terms in a 3 by 3. Negative in this case. It just depends on what these numbers are. But those negative signs and these positive signs have to be there. They're not part of the arithmetic. They're part of the definition of the determinant. Okay. Let's see here. Let's go over some properties of the determinants. Just like we did properties of matrices, we'll talk about some properties of determinants. So let A be an n by n matrix. Okay. And then the determinant of the A transpose is the determinant of A. In other words, if I take A, take the transpose of it, and if I take the determinant, it's the same as the determinant of A. No change. If you have a matrix and you interchange 2 rows or 2 columns, this way or this way, of the matrix, the determinant changes sign. So it goes from positive to negative, negative to positive, positive to negative, negative to positive. If 2 rows or columns of a matrix are equal, then the determinant equals 0. Nice and simple. If a row or a column of A is entirely zeros, then the determinant, again, is equal to 0. If a single row or a column is multiplied by a non-zero constant, r, non-zero, then the determinant is multiplied by r. The whole determinant is multiplied by r if one row or column is just multiplied by r. Let's do an example. We'll let A equal to 1, 2, 3, 1, 5, 3, and 2, 8, 6. Okay, we want to find the determinant of A. In this case, I'm actually going to write it with this symbol, and you'll see why in a minute. So I'm going to rewrite it. 1, 2, 3, 1, 5, 3, 2, 8, 6. In this case, using some of the properties, particularly the one where we say if we multiply by a particular constant, I'm going to use something that's going to be akin to factoring out that you're used to from algebra. That's why I use this. I want you to see all of the entries. That's equal to, so notice this is 286. You can divide this by 2, which means I can actually factor out a 2 from here. So I'm going to put a 2, and I leave the other rows the same. 1, 5, 3, and this becomes 1, 4, 3. Okay. I can factor out a 3 here too. So I have 2 times 3, 1, 2, 1. I can factor out a 3 from this column. 1, 5, 1, 1, 4, 1. Okay. Now notice, I have a column of 1s and another column of 1s. 2 columns that are the same. So now the determinant is equal to 2 times 3, and when I have something where 2 columns are the same, the determinant is 0. So, saved myself a lot of problems. I didn't have to go through that whole strange this diagonal, this entry, that entry, positive, negative. I used the properties of determinants to actually make my life a lot easier, and I was able to find the determinant of a 3 by 3 pretty quickly, just by some standard algebraic manipulation. Okay. Property number 6. If a multiple of one row or a column of A is added to another row or a column, then the determinant is unchanged. Remember that process of elimination that we did? We were doing Gauss-Jordan reduction, Gauss-Jordan elimination, where we multiplied some multiple of one row and added it to another. When you do that, you're creating an equivalent system, you remember, so the determinant doesn't change because the system is equivalent. Now, the 7th property, very, very important. If A is upper triangular, that means all entries below the main diagonal are 0, then the determinant of A is the product of the entries on the main diagonal. A upper triangular matrix looks like, let's just say 1, 2, 3, let's say 3, 4, 6. Everything, so this is the main diagonal, okay? Everything below the main diagonal is zeros. So notice 0, 0, 0, but there are entries on the main diagonal. Some of them can be zeros, but they're not all 0, okay? So upper triangular means the upper part, the upper right-hand part is the shape of a triangle. Okay? When that's the case, then the determinant is just that. It's kind of nice. So if you can, actually turn it into, by a bunch of manipulation that you do to matrices, our elimination, interchanging rows, multiplying one row by another, adding it to another row. If you can actually change it to an upper triangular matrix, then you just multiply those entries and you have your determinant. Let's do an example. Okay. I'll go ahead and put my determinant symbol right there already. 4, 3, 2, 3, negative 2, 5, and 2, 4, 6. Okay, I'm going to go ahead and factor out a 2 from the 3rd row right here. So that's equal to 2 times 4, 3, 2, 3, negative 2, 5, 1, 2, 3. Okay. I'm actually going to switch this row, the third row, and the first row. I'm just going to switch them. And when I do that, I change the sign of the determinant. So I just stick a -2 in front of that, and then I go 1, 2, 3. I leave the second row the same, 2, 5, 4, 3, 2. So these are pretty simple things that we're doing here. Okay, now I have a 1 here, and I have a 3 and a 4. I'm going to multiply this first row by -3, add it to this. Okay? So we end up with -2 times 1, 2, 3, 0, -8, -4, 4, 3, 2. Now I'm going to do the same thing with this row right here. I'm going to multiply this first row by -4, add it to the third row. So I end up with -2 times 1, 2, 3, 0, -8, -4, 0, -5, -10. Okay. I'm going to factor out, notice here, there's an 8, there's a 4. I'm going to go ahead and factor out a 4. So -2, we'll take a 4, and I'm going to also take out a 5 here, okay? 5. That turns it into 1, 2, 3, 0, -2, -1, and 0, -1, oops, that is a -10. If I divide by 5, that should give me a -2. Okay, so all I've done is factor out. I'm actually going to do one more thing here. I'm going to switch these rows simply because I want the one on top of the 2. Personal choice, I don't necessarily need to do it. So again, when I switch a row, I change the sign. So I get rid of that negative sign. 2 times 4 times 5, 1, 2, 3, 0, -1, -2, 0, -2, -1. Okay. Now, I'm going to multiply this by +2, this second row by +2, add it to this one to get rid of this -2. Okay, and when I do that, I get 2 times 4 times 5, 1, 2, 3, 0, -1, -2, 0, 0, 3. Now I have a upper triangular matrix. Zeros, entries along the main diagonal. Now my determinant is equal to 2, I'm going to skip the parentheses, times 4, times 5, times 1, times -1, times 3. So just this times that, and now the determinant of this is just the entries along the main diagonal, and I have just a straight multiplication problem, and I should end up with -120. So properties, I've taken a matrix, subjected it to a bunch of properties, simplified it a little bit in order to find the determinant. Okay. A few more properties to go. Number 8 is if I take two matrices and I multiply them and then take the determinant, well, it's the same as just taking the determinant of the first one times the determinant of the second one. So determinant of A times B is equal to the determinant of A times the determinant of B. Reasonably straightforward there. Now, if A is non-singular, if it's invertible, if I have the inverse and if I take the determinant of it, it's the same as taking 1 over the determinant of the original matrix. Notice, this is not, again, we're not talking about 1 over A. 1 over A is a matrix. Division by a matrix is not defined, but the determinant of A is a number, so division by a number is defined. Let's go ahead and do an example. We'll let A equal to 1, 2, 3, 4. We know that the determinant of A is equal to 1 times 4, which is 4, minus 2 times 3, 6, equals -2. Okay? Now, when we use our math software to calculate the inverse of this matrix, we get the following. negative 2, 1, 3 halves, minus 1 half. When we take the determinant of the inverse, we get minus 2 times minus 1 half, minus 2, I'll write this one out, times minus 1 half, minus 1 times 3 halves. Minus 2 times minus 1 half is a 1, minus 3 halves is equal to negative 1 half. Well, we said that the determinant of the inverse, we said that it's equal to, we want to confirm that, 1 divided by the determinant of the original. Well, the determinant of the inverse is minus 1 half. Is it equal to 1 over minus 2? Yes. So, if you want to know the determinant of the inverse, instead of finding the inverse and getting the determinant, you can just find the determinant of A and take the reciprocal of it. Again, this is not 1 over the matrix A. This is 1 over the determinant of A. The determinant of a matrix is a number. The matrix itself is not a number. And that covers determinants. Thank you for joining us at educator.com, Linear Algebra. We'll see you next time. Bye-bye.